In this video, we will look at an alternate way to determine the electron configuration, as opposed to the one in our previous video on orbital diagrams. Both are valid, and you should be able to draw your orbital diagrams before you do the electron configuration in this other manner. The reason for this is there is additional information in the orbital diagrams that is not fully captured in the electron configuration until you're very comfortable with doing them. There is an alternate method for determining the electron configuration based on the shape of the periodic table. The electron configurations themselves can actually be determined more easily by looking at the periodic table than is done from the orbital diagrams. The shape of the periodic table, with its high region on the left and the right and the low region in the middle and this block down at the bottom, actually come from the orbitals as they're being filled. The different sections are broken up into what we call blocks. The first two groups, as well as helium, are considered to be in the S block. When you are in this section or moving through the section, you are filling the S orbitals. The next section is the P block. Any element in this section is currently filling the P orbitals. Down here in the bottom, you are filling the D orbitals in the D block. And at the very bottom of the periodic table, we have our F block. So what you will do in order to determine the electron configuration is find the element on the periodic table and then go through the periodic table, the different blocks, in order to determine the orbitals that you filled in order to get there. A thing to note is that the S block starts with our n equals 1. So you have your first row of the S block is the 1s. The first row of the P block is the 2p. The first row of the D block is the 3d, and the first row of the F block is the 4f. Let's look at this alternate method in practice using a couple examples. So the first one, chlorine. Chlorine is located here on our periodic table. In our previous discussion, using the orbital diagrams, we would determine the total number of electrons, which is the same as the atomic number, if the atom is neutrally charged. So in this case, it would be 17, and then you would fill your blocks. In this case, we look at where we are, and we write down the orbitals that we had to fill to get there. So for chlorine, we've gone through our 1s orbitals, where helium is counted as being over here. We've gone through our 2s orbitals, and we've gone through our 2p orbitals. We then went through our 3s orbitals, and we are in our second row of our p orbitals, where the first row is the 2p, so the next row, the second row of the p would be the 3p, and then we just count in how far we are. We are 1, 2, 3, 4, 5. We're 5 in to the 3p orbitals. So we would write this out as being 1s2, because we went through the 1s, 2s2, we went through the 2s's, 2p. The p's, there are a total of 6 electrons, so we would have 2p6. Then we go through the 3s block, 3s2, and then we're 5 electrons in to the 3p's, so 3p5. That is the electron configuration. If you do this using the orbital diagrams, you will come out with the same configuration. Now for iron, iron is located here. So if you were using orbital diagrams, we would count out 26 electrons in our filling of our blocks. But using this method, we just go through the different blocks and figure out which ones we've passed through in order to get to iron's location. So to get to iron, we go through the 1s, we go through the 2s, we go through the 2p, 3s, 3p, this is the 4s, and then we're in the 3ds, and we are 1, 2, 3, 4, 5. We are 6 into the 3ds. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d 3p6 would be our configuration for iron. Now for selenium, selenium is located here. So it has 34 electrons. We figure out which blocks we've gone through in order to get to selenium. So that'd be the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and then there's 10 in the d block. And then we are 1, 2, 3, 4 electrons into our 4p. So our configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, and then we were 4 in, so 4p4. Krypton is only a little further along the periodic table. So to figure out our configuration, we need to know what blocks we've gone through. We've gone through the 1s, the 2s, the 2p, 3s, 3p, 4s, 3d, and then we are working on the 4p orbitals, and we've gone all the way through, and we're on the last part. So we're ending with 4p6. So our configuration for krypton would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. For our last one, praseodymium, it's located down here. Figuring out the blocks that we've gone through to get there. We've gone through the 1s, the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Then where your bottom block here starts, this one here corresponds to coming right after your S block. So it starts right here. So we've done the 1, 2, 3, 4, 5, 6. We're just finished the 6S. Here we're in the 4F. We are 1, 2, 3 in. So that we'd be ending with 4F3. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then 4f3. Now you might have noticed with that last example, writing out the full electron configuration did take quite a length of time. Because as you go further down the periodic table, it can be a bit tedious to write out the full electron configuration. There is a shorthand method that is based on the noble gases and their fully filled electron shells. So if we look at zirconium as an example, zirconium is listed down here. Okay, so the full electron configuration for it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. If we compare that with krypton, the previous noble gas, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, you'll notice that they are the same up till the end of the krypton configuration. The beginning part up till the end of the 4p6, krypton and zirconium have the exact same set of numbers. So what we can do is, for our shorthand notation, just say use everything that we find for krypton, and then add on to that the extra bit that we find for the zirconium. Right? So krypton is the equivalent of saying 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Zirconium has 4 additional electrons, which would be the 5s2, 4d2. So the way that you will write out these shorthand notations is to take your previous noble gas. So you'll take, let's say we have zirconium, you'll go up one row and then look down to the right and find the previous noble gas. You'll write that configuration out, and then all you have to do is say what blocks you've gone through to get to your current location. Right? So it makes it much easier to write out. You just say krypton, in addition to krypton, we had the 1, 2, 3, 4, 5. Your s block starts at 1, so this would be the 5s. And then your d orbitals, they start out at 3, and then they go 4, so this would be the 4d2, which is the configuration that we have there. As is often the case when you're attempting to model reality, there are going to be exceptions. Thankfully for the electron configurations, there aren't too many exceptions, and those exceptions occur for a reason. Now, there is a small stabilization that comes from having half and fully filled orbitals within a particular subshell. Because the ns and the n-1d orbitals are so close together, and by ns and n-1d, what I mean, for example, is the 5s and the 4d. So your n is your principal quantum number. The orbitals, if you remember, the d orbitals are only slightly higher in energy than the next level up of your s orbitals. Right? So the s orbitals for the 5s are only slightly lower in energy normally than the 4d. So because these two are close together, sometimes you'll have situations where it is more stable to have the half-filled s orbital and a half or fully filled set of d orbitals in that particular subshell. So some of your transition metals are going to have irregular electron configurations, which may look anomalous, in which the ns, the particular s orbital, the outermost s orbital that has electrons in it, is going to be partially filled, and the n-1d, so the d orbital that you're working with, is going to be either half filled or fully filled. Some examples of these are chromium, molybdenum, copper, and silver. Note that these anomalies happen when the s electron jumps into a d orbital to create either a half-filled or fully filled sublevel. So for our chromium, what we would normally expect, based on its location, it is 4 spots into the d block. So what we would normally expect is that the electron configuration would be our previous noble gas, argon, with 4s2, 3d4. But because the d orbitals, if we can half fill them, there's a stabilization that occurs from having them fully half filled. The electron in your 4s orbital will actually move up into the 3d to give a 4s1, 3d5. You get the same thing for the molybdenum. The difference being that it is the 5s and not the 4s, and then it's the 4d and not the 3d. But it's 5s1, 4d5. So the chromium column is the one that has the exceptions. Another one is your copper column. So copper can actually get a fully filled d subshell by taking an electron from the 4s orbital and kicking it up into the 3d. Similarly, silver can also have a fully filled d block by taking an electron from the 5s and kicking it up. Now, looking through this configuration, you might notice a couple other exceptions. However, The ones that we will be primarily concerned with are the chromium and the copper columns, because they occur for a constrained, narrow reason of having the half-filled and fully filled shells being more stable, which we will see again when we're looking at ionization energies. So again, the exceptions follow a very narrow group in which you have the chromium column here and the copper column. So what we would expect from these, if we weren't taking into account the exceptions, would be that we would expect the chromium to be argon core with the additional 4s2 3d4 added on. What we see experimentally is that it is an argon core, but it is 4s1 3d5. Similarly, molybdenum, which is right below chromium, we would expect it to be krypton core 5s2 4d4. But experimentally, we can determine that it has that krypton core, but is 5s1 4d5. You have a similar thing occurring for the copper and the silver, where for the copper you expect it to be argon core 4s2 3d9, but experimentally it is argon core 4s1 3d10, and then for silver we would expect it to have a krypton core 5s2 4d9, but you actually find krypton 5s1 4d10. So what are some of the implications of our electron configurations and those orbital diagrams? Well, from the orbital diagrams, and once you are well practiced with the electron configurations, you'll be able to tell whether something is paramagnetic or diamagnetic. Paramagnetic is when you have an electron configuration that results in unpaired electrons. What this means is that atoms or ions will have a net magnetic field. This is what we refer to as paramagnetism. Because they have their own net magnetic field, they will be attracted to other magnetic fields. What this means is that silver metal can be expected to interact with a magnetic field. On the other hand, electron configurations that result in all the electrons being paired mean that the atom or ion will have no net magnetic field. This is called diamagnetism. In fact, these diamagnetic atoms will be slightly repelled by a magnetic field. So what we would expect is that metals like zinc will actually not stick to a magnet. In fact, they will be slightly repelled. So the way that you'll be able to determine if something is paramagnetic or diamagnetic is look at your orbital diagrams. In the last orbitals that you're filling up, are there unpaired electrons? If there is a single unpaired electron, then the atom or ion is paramagnetic. If, on the other hand, every single electron has a pair, then the atom or ion will be called diamagnetic.